Awesome. Welcome, everyone. This is another fun adventure with our cool friends from all around the world today. This is Deep Learning Adventures, a fun and engaging meetup. We talk about data science, deep learning, and anything related to TensorFlow for the last, I think, couple of months, right, Robert? My co-host and great friend Robert's joining me today. Our friend David is not feeling well. Hopefully he recovers soon, as well as my great friend Dimitri, who will cover a session for us. But I'm humbled and excited to see friends from all around the world, from Mexico City, from Germany, from India, from US, obviously. So thank you everyone for joining us. It really means a lot to us. For you watching us offline, hopefully you can join us one day. We maybe as our community grows, maybe you can have a different session on different time zones so that people from other parts of the world can join us. I know for sure I'll be traveling next month to Europe. It'll be a little bit of a challenge for me for 1 month, but I'll try my best to join on time. Cool. That said, Robert, did you have anything to say?
Just wanted to announce that we are wrapping up the deep learning adventure data and deployment from TensorFlow. We have been covering this course, going through the material really pretty quickly right after we finished the material in the course ourselves. So we'll be presenting it to you, but this is a community of learners, and none of us professes to be the expert in anything. So please, if you have anything to add to the discussion or you want to ask questions, I'd like to make that as open a floor as possible. That being said, we will share our learnings from the course and hopefully give those who haven't used these tools before an appreciation for the value that they could provide and an understanding of what situations they might be most useful for your own work.
Cool. I can share my screen. Thank you, Robert. I just wanted to start with this attribution page that we do. We're going to look at some materials today, and most of them are coming from both Coursera and Deep Learning AI, really great resources and platforms that allow learners like ourselves, the practitioners, to embark on new adventures, new journeys in data science and deep learning, as well as other fields as well. So a lot of the code that we're going to see today is actually developed by Deep Learning AI and Coursera. The other thing I want to mention is the specialization for those of you joining us for the first time. We started this journey, I think a couple of months ago, if I'm not mistaken, on advanced deployment scenarios with TensorFlow. This is covered by Lawrence and Andrew Ng as well. It is made up of 4 courses. It starts with, sorry, this is the specific last course. I want the specialization, there you go. So we started back in the days with browser-based models. We developed models and we deployed them on our browser with tensorflow.js. Then we shifted gears. We developed, we trained models and we deployed them on smaller devices like TensorFlow Lite, like Raspberry Pi, as well as Android and iOS devices. That was a fun course for us. Then we switched gears completely. In the past, most of our adventures, we focused heavily on the modeling part, accuracy, precision, how far are we, if it's a regression problem or a classification problem. But then in course 3 of the specialization, we really took a deeper look into the TensorFlow ecosystem, and specifically what kind of data sets we can use as inputs. It could be text, could be images, it could be CSV, structured data, NumPy, pandas, TF records, and how do we efficiently pre-process that data? How do we efficiently apply what are called different data pipelines? How do we access existing data sets within the TensorFlow ecosystem? And how do we prepare that for serving in our model? So that was the purpose of this 3rd course on data pipelines with TensorFlow Data Services. the last course that we are wrapping up today is we're covering what I call some advanced deployment scenarios, and we started last week with TensorFlow Extended, which is basically a platform for you to deploy production level machine learning algorithms and projects, including the data pipeline that we saw in the previous course, as well as some cool resources like TensorFlow Hub, where you can find pre-trained models. You can find what are called feature vectors that do the heavy lifting of, given an input, give you a rich set of vectors that, if it's a text-based, could be some kind of high-dimensional word embedding, or if it's an image-based input, it could be some kind of feature extractor. And you can use that and build your own neural network on top of that feature extractor to solve whatever problem you might have. Today, we're going to cover two slightly different platforms. We have come across Tensorboard in the past, a little bit, specifically the profiler plugin of the Tensorboard. So Robert and Dimitri are going to cover that for us. I'll cover the very last topic on federated learning and how can we learn from distributed devices in a way that preserves the privacy of the data of users. So that's the very last topic of this specialization. Cool. With that said, I'm going to stop sharing and I'll hand it over to Robert.
Sure. I also want to talk a little bit about upcoming events with Deep Learning Adventures and some plans, and we'll be soliciting some ideas from you all as well. So as this is the end of the data and deployment adventure, we will wrap that up tonight and do a happy hour next week. Great to see so many new folks online right now. We hope that we can get a chance to meet and chat with you, learn a little bit more about your experiences with machine learning, deep learning, your backgrounds and interests next week. I'm not sure that we've announced them on Meetup yet, but we will post this time next Wednesday, happy hour, which is really just an open, unrecorded session where we can all talk about problems of interest to us in this community. And after that, we will be doing a series of several challenge problems and other coding exercises. If anyone in the community has ideas for topics for that, please feel free to share them. Let us know. We are very interested in what you all might want to learn about as well, and we're looking for ideas for that. I know George has a couple of other ideas related to that, and maybe some other talks. I don't know if you want to preview any of that here, or if we should wait on that.
I can preview here. Actually, this is a good spot, and I appreciate you giving context. So yeah, the goal is, especially for you joining us for the first time, is we try to learn a new tool, a new technology, a new platform. By itself, that journey has some coding exercises, but as a community, we also try to fork our own path in this journey. So we're going to take an interesting data set, we're going to take an interesting approach, and really our goal is to touch upon the different courses and different concepts that we learn. Could it be deploying a model on an edge device, or could be maybe using an interesting data pipeline that does highly efficient data pre-processing for a model, or it could be maybe using things like Tensorboard or Tensorboard Hub, or even federated learning. In the middle, that's a little bit more on the research side. But really, as long as we touch one or two concepts of what we learned in this specialization, and we create our own project and we work as a community, that will be a very good follow-up to this specialization. And after that hands-on coding session, which I think will take like maybe 2 weeks, 3 at the most, we plan on having 2 guest speakers. One of them will be talking to us. He's from the Kaggle data science team. We've had the data scientist from Kaggle joining us in the past. This person wasn't available at that time, so I'm hoping he will be available again. He will talk about privacy preserving machine learning as well. He's working on some interesting projects. And I'm hoping also to have Lawrence, the instructor of the course as well, chat with us. We learned a lot in the specialization. We've gathered a lot of feedback for the course. We'll be sharing that with him and his team. Also want to chat, just an open discussion about what we learned, what we found interesting, what we thought could be expanded a bit more, and so forth. We enjoyed talking to Lawrence in the past when we took another specialization with TensorFlow, so it's very easy to talk to a person, and looking forward to having him again. After that, yeah, the floor is open, the sea is open, and up to the next adventure that we as a community decide to.
Yes, feel free to reach out, join us on Slack. I think George will post the link here shortly.
Yep, let me do it right now.
But we'll get started with the content for tonight now. So I'll be speaking briefly. Excuse me, Vladimir.
Yeah, go ahead, Vladimir.
Because we're on this topic, so we have, let's say, studied TensorFlow in pretty much detail, but PyTorch appears to be something that a lot of people use because it's simpler to use and it's kind of more accessible, let's say. Do we have any kind of strategic plans, let's say in the next half a year or something, to get to PyTorch?
Right. Have we ever done PyTorch? I'm trying to remember. I don't think we ever covered PyTorch. I know Robert mentioned it in the past that
some of the Coursera courses use PyTorch.
Oh, they do. Okay.
Instead. But these ones that are offered through Google, it's not surprising that they're on TensorFlow.
Right. No, we don't have like an exclusion or inclusion list. Yeah, it would be nice to cover maybe a PyTorch based specialization or topic or coding challenge. We just have to figure out a way to introduce it to the community so that somebody who knows a little bit about coding and machine learning, like us, I mean, we know a lot about TensorFlow for sure. So for us, converting to PyTorch, I wouldn't imagine it would be a challenge, but somebody who just joined us, what is a good way to introduce them to PyTorch?
Yeah, as Vladimir mentioned, it is a different user experience, especially at the beginning, and many people find PyTorch a little bit easier to get started.
Mm-hmm.
So
yeah, it is on our list. We're open to ideas how to introduce it.
So George, so to interrupt George, so I have a question here, right? Like, when we use Google Colab as a IDE to do any deep learning projects, and when you use a host runtime as a GPU, it's work fine. And when you use TPU as a runtime to change it, the processing of the particular projects will take some time. What is the reason behind that? You got my question?
Yeah. So you're saying that when you use Colab with TPU versus GPU, usually your training is a little bit longer?
Yeah. Yes, correct.
I think there are a couple of reasons for that. One is within Colab, you're getting a shared TensorFlow processing unit TPU, and you're sharing it with others. I mean, it's basically for free for you. So I don't know if internally the Google team has some kind of RAID capacity limits in the back end. But the other thing is TPUs are extremely data and power hungry. So setting them up, especially in the beginning, like we've seen that in previous projects, takes a few seconds just for them to be ready to consume data. And the other thing is usually when we work with TPUs, we work with very large data sets, like specifically not in regular formats, but like TF record formats, which has its own structure. So I would say a combination of infrastructure within Colab as well as the large data sets that we use.
Yeah, even we use Google Pro, like Colab Pro, the situation is the same. Like.
Oh, really? Okay. I'm surprised.
Because when you use multiple collabs, obviously it will slow down your process, right? If you use single one, then it will be fine. But when the Pro, if you use large data sets, it's the same. Like it's again, if you select TPU, the same slowness comes up.
Right.
So what do you recommend? What do you recommend to use? Like VS Code will be better, like or.
Well, the ID, it's not the ID, right? You have to rent a visual from Google Cloud or from other cloud providers, and they also have their Jupyter notebook version of Colab. I haven't personally tried that. I've used their virtual machines in the past with GPUs. It was running much faster than my local GPU, but I don't know, with TPUs. And Vladimir, what you were saying?
Okay, thanks, George. Yeah.
So yeah, so I actually I want to sorry to interrupt again. It's today's kind of I don't come very often. That's why I think I deserve more time. Sometimes I go, okay. Sorry, I just want to have something with my experience. I don't know that much, but okay. So the TPU from the start is has multiple cores that you can individually use. And let's say TPU version 2 comes in, can be 8, 32, I think 16 or something. Version 3 is the same story. So when you write your code, you have to write it specific. So first, in order to use the cores of the TPU, you have to use distributed training from the start. With the GPUs, you don't need to do this. You just say, okay, I want to use the GPU, and you fit, you do model fit, and it goes there. You just send the data, and the GPU figures out how to do it when you use a single GPU. And what happens on the call-up, it's you usually have one GPU. But for the TPU, one GPU has multiple cores. And in order to exploit the parallelism in these 8 cores that are in the TPU, you have to start distributing from the start. That's one. Second, you have to write the code specifically, so you cannot use this mirror strategy, this is the standard one. You have to use TPU mirror strategy. So what happens is that when you train with the TPU, you don't have, let's say, the parallelization we're talking the last course, the previous one also. You pipeline the CPU and the GPU work. So you have, let's say, you parallelize them so that the GPU doesn't wait for the CPU. Here you parallelize not only the TPU with respect to the CPU, but also the cores of the TPU themselves. And in this case, you can get this is the way to get let's say comparable performance, at least with the GPU. So on the call up, I have also noticed this. So if you just read the code on TPU, you have the same code. You say, okay, I want GPU, and then you say I want TPU. It's much slower. I suggest there is. I will look it up. In one of the courses of Lawrence, he talks about this exactly. Well, no, not exactly this, because they don't really want to. But say, okay, if you want to use TPU, you have to do it in this way. You have to write your code in this way. Roughly the story. It's. I don't know whether we have gone through this. Maybe I can look it up exactly which course was. But there is distributed training or something like this, and one of the weeks is GPU, and the next one is TPU. And there you can look these things up. I have done on the GCP their example with TPU. It's blazingly fast, but you have to just use properly the TPU. The downside is because we were also trying the same thing when it worked.
Yes,
we want
yes,
to have
yes.
the same code and
Got
bring
it,
the
got it.
TPU, the GPU, and then you want to do it DPU and say yes. Well, so far I haven't found a way to do this. So just to if you find, just let me know. But so far we kind of gave up on the TPU because you have to maintain 2 pieces of code. Now on GCP, I don't know whether you know the story. They kind of stopped giving GPUs unless you have a business account. But you can get the TPU. Let's say you open a trial and things like this you get the TPU without a problem. So to me, at least, it looks like the Google is trying to promote. I mean, they want to make money out of this. I mean, these TPUs have been around like 7-8 years. So they're kind of promoting the TPU. That's my understanding. The problem is, if they make it so that you don't have to change the code, I'll gladly do this. But if I have to change the code, I don't know. So far, I have this dilemma. If anyone knows anything about this, how to do this, let me know, please. I'll be happy to discuss what I found also.
Thank you, Vladimir. We've had conversations on these topics in the past, but I don't think any of us is an expert. There's a lot to learn from just trial and error on this kind of thing. Happy to have this discussion. Certainly something we should keep talking about. Since it's 7:30 our time now, I think we'll move back to the content planned for this evening, which is Tensorboard and Federated Learning.
Yeah, before we do that, can I just share one screenshot just for Kiran here? So yeah, in previous sections, we covered this cool plugin from Tensorboard called Tensor Profiler.
This is the profiler, and this is part that is not in the material for tonight, but it's related. And I know you and maybe Dimitri have some thoughts to say on it anyway.
Yeah, but I mean, we've had some challenges. We'll talk on those, on how to make it run locally on a Colab. But the good thing about this is that it tells you if your pipeline is input bound, meaning most of the time is spent on input, and it gives you recommendations on what to do. And Robert and Dimitri did an awesome session a couple weeks ago on where to look for optimizations and how to basically parallelize the CPU and the GPU coordination, or in this case, the CPU and the TPU coordination. So I think that's one approach I would go with.
That's great, George. Yeah, I'll look into this. Thank you.
Yeah, you're welcome. I'll share the link. Sorry, Robert.
Okay, can everyone see my screen?
Yes.
Wonderful.
Yes.
So we'll be covering the third week of this course, the TensorFlow data and deployment. This is week 3 of course 4 of the 4-course specialization. And what we're looking at here is an overview of the topics for this week. And this week we'll be talking about Tensorboard, which is a suite of tools to help inform you while you are training and or developing your models. And this is really just going to be a very quick overview. I would say high level, but there's a little bit of code that we'll go into too. There's a lot of capability with this suite of tools, and we'll only explore a small part of them. There's documentation on Google that goes into more detail than the course does and shows many more examples of use cases. But I think that the short material in the course does give you an appreciation for the types of feedback that you can get from utilizing a tool like Tensorboard. So in the course, they're going to present 2 ways of deploying Tensorboard, if you will. The first way, because it's the easiest to get started using, is tensorboard.dev, which is a site where you can actually share the model performance, current results, debugging information, hyperparameters, visualizations of a variety of things that we'll show you. And you can collaborate by sharing and iterating and looking through these objects that are available for your entire team to inspect on a public website. So note that it is a public website, so certain models you may not want to share there, but that is a tool that is very useful for other projects. And then later we will also go into the implementation of local Tensorboard, which basically just means running it on your own machine, and instead of piping the results to a website where other people can see it, we're going to be looking at the results as objects within our Jupyter notebooks. And then they go into an example that goes a little bit beyond the basics to show you how you can do more general tasks with the Tensorboard tool. I downloaded a few screenshots from the course. Before we get started, let's listen to a little bit of the intro video that Andrew and Lawrence prepared for this week. I think you'll see a little bit of their sense of humor, if you will.
Welcome back. In this week, you learn about Tensorboard. Tensorboard is not about when Lawrence or I are talking about tensors and you go, this is really not interesting. I am so Tensorboard. Tensorboard is a tool that you could use to help train your deep learning models. What is Tensorboard?
It's a tool that you can use to help train your deep learning models.
It's not a state of mind.
It's not a state of mind, and it's a couple of things. That's a suite of tools that will really help you when you're training your model. So we'll give you things like visualization so that you can see your accuracy and loss over time. Or you can share images so that even if it's just a simple look at the images that you're training an image classifier on. There's also the model structure. So you can explore your model structure and see how that looks. And there's just a whole bunch of tools that allow you to inspect and debug your models while they're training.
So we'll go through a few of the examples that they show here. So I put a couple of shots of the overview there. As Lawrence just mentioned, the highlights here, Tensorboard is a suite of tools. It's going to help us engineer and iterate our models better. We're going to get visualizations of training progress, a lot of things that we've seen previously just by manually plotting them. Tensorboard offers a lot of this stuff automatically. You can get visualizations, you can get a view of the flowchart of your model structure, you can see the distributions of weights and biases or activations that your network is producing as a function of what training stage you're at. And depending on your problem, these things can be very useful in debugging various issues that you might experience with your models. This is a screenshot from the basic example at tensorboard.dev, but I think I'm just going to go right over there and we'll walk through it together. So right here we have a interface here with get started. This one will lead to an example collab, which we'll go through shortly. First of all, let's just look at the experiment that they put in place, the default experiment, just to get a sense for the types of stuff that can be produced with very little extra coding. So we can view things like the accuracy of the model, cross entropy loss. I don't even know, did they say what model, what data set we're even looking at? I think we're looking at fashion MNIST here. I can't recall though. A lot of tooltips hovering over. I don't know if you can see. We have a variety of things for affecting the charts themselves. You can smooth, or the opposite of smoothing there. If you want them smoother, you can look there. You can select the training runs down here. Rescale the horizontal axis depending on clock time, wall time, relative time, etc. Another tool that Lawrence briefly mentioned there is the graph output, where you can see your model structure. And here you're looking at the model bottom up, the lower level layers, the convolution here. You have fully connected layers here. You can actually see all the activations, various attributes of objects. Here's where you're implementing the loss function once you've actually come out of the final output. And then you've got accuracy computed as a metric. I personally, after having looked through so many model summaries on TensorFlow and seen very few of these objects, I find them harder to understand than just looking at the tables that TensorFlow outputs. But I'm sure there are people that have the opposite experience. So this could be a really useful way for some to visualize the model to make sure that it's doing what you think it's doing. These are pretty cool, and you can turn them on. You can enable them with just one extra parameter that you send to the callback function that will show for Tensorboard construction. And right here, what we're looking at is the activations and biases and weights, I think, down here. Yep. For each of the layers, I think we have conv1 there, but maybe we have other conv2 down here, activations, weights, and you can open up these other ones interactively down here. A lot of interesting things that you could learn from your models this way. One thing that we can see here, which I thought was a little bit surprising just based on the way models often train, is that the biases here start out kind of high and seem to be trending back towards 0. One thing I didn't mention is what the axis coming in and out of the page is. This is actually a training epoch or time or batch, depending on how you're displaying it. I think it's epochs here, but it's essentially your time axis. Right here you have whatever quantity you're looking at, and then the frequency is plotted up there. You can also visualize these same sorts of distributions in two-dimensional figures. They may be more interpretable for some. I think I like the histogram visualization here a little bit better. There's also a pretty cool tool here which can enable you to organize your experiments. A lot of times when we come up with lots of ideas to try different things, try different hyperparameters, the number of possible tasks quickly grows exponentially. So it can be very useful to organize your own experimentation, to have tools like this where you can quickly plug in a certain result, and then you have these trial IDs here, which I guess link back to something. I'm not really sure where that goes. Show metrics. Okay, we've got each trial. We can see certain metrics right in here. Accuracy, I guess we can plot it on different scales. So a lot of stuff here that comes with the model straight out of the box. Not much extra coding. You really just have to turn on some of these extra tabs here. We'll also show a little bit on how to make your own custom figures too. So this was the default example shown on Tensorboard.
Question, Robert, the H parameters, was it some kind of hyperparameter that you tried different values? Is that what it was?
Yeah, so it's really just a summary, a tool to help you keep track of your experiments.
Oh, okay. Oh.
So right here we've got what different learning rates. This might be a little bit easier to visualize if you put this in log form.
So you're going with
you're not counting zeros.
With a large learning rate, and you're making it smaller and smaller, and you see how that affects your performance.
Yeah.
I like the coordinates view where you have everything in one page, where you can see for different combinations of hyperparameters. How do you see the performance here? Is that the color? It's a if you mouse over, I think.
Where are we going?
Yeah, if you hover over any of the lines, it should tell you the accuracy. Yeah, okay. So that's one specific combination. So learning rate is 0.0001. FC, is that the activation value for after FC, I guess? I'm not sure what that is. Conv accuracy.
I think that might just be which layer. Actually, I'm not sure.
Oh, FC2. Yep, FC2 probably. Conv2. Accuracy.
Yeah, so this model had 2 convolutional layers and 2 fully connected layers, and I think these 2 figures here are just telling us which layer we're inspecting.
Right. So there's one specific path that has accuracy.
Or no, this is the number of layers. I'm sorry. This one had 2 fully connected layers, and this one may have used 1 convolutional layer, and that one used 2 convolutional layers.
So there's one that had like 99% accuracy or 100% accuracy. You can trace back to see where that came from, I guess. Yeah.
Yeah, they're not indicating here whether this is in sample accuracy or out of sample.
Cool.
I don't know. And then you can also get these things returned to you as a JSON, which could be useful in some cases.
Nice.
So going back to the home page, you also have a little tab up here that says My Experiments. And once you've gone through the tutorial, you'll have your first experiment. And if you click on that, you'll get experiment name. And you can add and delete experiments at any time. You may have your currently running experiments shown here in a list. And you can click on, this is just the simple example that the introductory collab produces. So let's walk through that collab, and then we'll look at this set of charts. So we're looking at getting started with tensorboard.dev, and this case, in this collab, we will be uploading to tensorboard.dev. I'll go through this one, and then we'll get to this other notebook here where we'll do a little bit more complicated task, but we'll keep it local. And by local, I actually mean within collab. So as local as that might mean.
Do you mind closing the table of contents, Robert, just to get some more real estate?
Yeah, sure.
Thank you. Yeah, that's perfect.
So here we're going to be looking at the MNIST dataset. This is the handwritten digits that we're all familiar with. We're going to load it just straight from Keras datasets, MNIST. We're going to scale it to from the 8-bit integer down to a float between 0 and 1. We're going to define a simple model here. It's not a convolutional model at all. We're immediately flattening the image to a 784 dimensional vector and then feeding it into one dense layer, putting a dropout with 20% probability in there, and then our dense layer at the end is going to give us 1 of 10 classes with the softmax activation. So to get the simplest tensorboard, what you're going to need to do is construct a callback. And the simplest way to do this is to take advantage of the tf-keras callbacks tensorboard function. And all you have to tell it to do is tell it where to log the files that it's going to produce. And this argument I think is optional, but a histogram frequency equals 1 will tell it to produce these visualizations of weights, biases, and activations at a rate of 1 per epoch. If you put in a 0, or I think if you leave it, I think the default may be 0. Don't recall, but it is open right here. So yes, histogram frequency equals 0 by default. And this is the basic callback that is capable of building this style of tensorboard. We won't go through the other arguments. The course really doesn't mention them too much either. The basic usage, as we said, is just callbacks.tensorboard. Specify the log directory, this is a typical place to write it on your machine. And then when you fit your model, you're going to give it training data, images, and labels, number of epochs, and then you just have to include your tensorboard callback as one of the elements of the list within callbacks.
Can I ask a question?
Sure, Harold, go ahead.
Yeah, my course has a different optimizer that we use and that they recommend using. I noticed back earlier it was ADAM. Was that just part of your course that they recommended using that?
There are a number of different optimizers. SGD is a common one. It's maybe the simplest one. Atom is a bit of an optimization on that takes advantage of momentum and other characteristics to make better guesses at each step. For the purposes of these demonstrations, I think in the course we're usually using Atom, not SGD. We'll see right down here. Where is it? Yeah, optimizer is Atom in this one.
Yeah, my course, I don't know if you're familiar with RMS prop. Was that they said, or at least the book that we were using recommended using that one always, but obviously there are a couple different ways to compile your model and create your model.
Yeah, optimization, just finding that next step, how to make the best guess on the next model is a really important topic. I'd just I'll defer that, and I think we could have a much larger discussion on that. I think for the purposes of the material here, it's not going to matter much which optimizer we select. In many cases, it won't, especially for these simple examples. Choosing Atom is usually a great option. It's adaptive, so it's a little bit more likely to work because you don't if you're making poor guesses on the parameters, it will adjust those hyperparameters to account for the conditions you're actually facing. RMS prop takes advantage of momentum. SGD is a little bit more low level, just take a step based on the most recent gradient measurement. But that's a fascinating topic, but I'd rather not delve too deeply into it right now. But let's definitely have that discussion on another day or on Slack.
Robert, just one point. ADAM includes RMS prop and gradient descent with momentum. It combines the two together. So the question about RMS prop, don't worry, ADAM takes care of it. Whether you want to use only RMS prop, that's it. It's a combination of the two.
Awesome. Thank you, Vladimir. So here we're just writing our Tensorboard logs and giving it a string down here just to make sure that each log is going to be a different value so they're not going to overwrite each other. And in this case, we're passing callback Tensorboard log directory. We're going to give it a histogram frequency 1, so it's going to write out one. I think it's going to take one snapshot of the weights and biases per epoch. And then we're going to do this hyperparameters callback here too. So this is already a little bit beyond the basic because we're using a second callback. This is a Keras callback, and let's see, we're just going to tell it that the number of ReLU units is 512, dropout 0.2. I think that's just for summarizing the state of the hyperparameters so that we can see that table there. It's not part of the basic Tensorboard callback, but it's a pretty easy one to implement here to track the parameters, the hyperparameters of your model. So if you are running this on Jupyter and you want to send your model over to tensorboard.dev, what you may need to do is authorize that in your shell console outside of Jupyter. If you're in Colab, you'll actually just get prompted to do that directly from the notebook itself. That's the way I completed this notebook. What we're doing here is, this is important for the tensorboard.dev option. You're going to upload it to your log directory here. This is just a shell command escape, and this is the name you're giving it, description, and it's going to do it in one shot. And then when you navigate to the experiments, this is what it will look like. We can see it over here because we are already navigated to the experiment. So those were screenshots, but we'll actually get some tooltip information here too. Just curious, are you able to see when I mouse over these things, do the tooltips come over Zoom as well?
Yeah, blue is training and red is validation run.
Yeah, great. So here we have 5 epochs labeled 0 through 4 as specified by our histogram frequency equals 1. We're going to get 5 epochs worth of lost data, and we have, I think we're also looking at it versus iterations here, just versus number of training steps that are taken. Multiple training steps taken per each epoch, of course. We can, the same functionality here. We can download the data itself, which I can't recall if that's a figure or the actual data. I think it's just an image. And then we get this model graph here from the model that we built over in the Colab. Pretty complicated looking for such a simple model. As I said, I find these graphs to be more difficult to use than the summaries.
You can zoom in, right? You can even expand specific parts of the graph.
Yeah, you can zoom in. I did that before. How do you do that?
I think just with your fingers expand or click on any of this.
You can click on nodes and get certain information here. Sequential might tell us it was a subgraph of 20 nodes, which includes optimization, loss function, all kinds of things.
Cool.
We get our distributions, just 5 epochs again, but we can see how the biases here are growing. They start at 0 and are expanding outwards. After the first epoch, they're here. After the 5th epoch, they're a little bit more widely distributed. View the distributions. Our experiment log, we've only done one set of hyperparameters here, but we've noted that we're going to track the number of relu units and the dropout. Those might be things that we're going to tweak. And text data, we haven't written JSON, so that's not going to show up. Any questions on this one before I go through the other Colab, the local version?
I love the distribution page or histogram page where you can see how stable your model is, right? You can see most of them during training, the weights and biases that are like around specific, especially on the right, like bell-shaped curve. They're not, your model is stable, right? It's not misbehaving.
Mm-hmm. The other notebook here shows some pretty cool customization that you can do and may give you some ideas on how you might redesign some of these features to suit your own case. Here we have image data that we're looking at. I think this is the one where we're going to get into the fashion MNIST model. So TensorFlow has an image summary API, and what you can do with that is you can take the tensors and really any arbitrary images and just view them directly over in Tensorboard. You might find this a lot easier than viewing them in your notebook interactively. It also will store them so that you can come back and look at them after the experiment is run with that interface that you can click through each one. So here we're doing some of the same imports, a few extra things this time because we're going to be looking at a different problem. We're going to be importing scikit-learn metrics. In this example, we'll be looking at fashion MNIST and drawing our own confusion matrix from scratch. Using that scikit-learn metrics confusion matrix output, we'll be converting that into an image and then displaying it in the Tensorboard, which is not something that Tensorboard is natively configured to do, but they provide a few helper functions here that give you an idea of how you can customize this tool to produce more useful outputs for a specific use case. So fashion MNIST, you may be familiar with, is very similar to the MNIST dataset in size and structure. The images are the same size, 28 by 28. There are 70,000 images, which I think is exactly the same as the number in MNIST. We've got 60,000 in a set called training. We've got 10,000 images in a set called test. And we will load the data the same way that we did the other one. Here we're going to inspect it a little bit more closely, so we'll take a list of the names of the classes as well. If you're not familiar with the data set, it might be useful to see an example. So we're just going to pull the very first image from the data set and look at its shape, 28 by 28, so that checks out with our expectation. It's an ankle boot, and the class number is 9. And then we're going to print out, I think we're going to visualize the image here. Maybe we don't do that until the Tensorboard. Yeah, that's what we're doing. So image NumPy reshape train images. We have to reshape this because the image summary API expects this to be in 4-dimensional format where the first dimension is a batch size. So if we're going to send it a single image, we need to essentially expand the dimension there so that we have a 1 by 28 by 28 by 1 output. This last dimension of 1 is the channels, but these are grayscale images, so they will not have a color dimension. So you're clearing out prior log data, you're creating your new log directory, and you're going to write out this summary.image. And the image itself, because it's a tensor, it can be written directly out with tf.summary.image, and we can visualize it directly in our Tensorboard under the Images tab. You get some tweaks you can play with here, make the image brighter, contrast. You would be able to toggle all runs, but this is the only run that we've got. So you can also visualize multiple images here, and the way to do that is to basically pass it more than one image. So instead of just the first image, we've got 25 images now. And by passing train images up to 25 and reshaping it this way, the -1 will tell it to put the extra dimension here, which is going to be 25. So we're going to get this batch of 25 images. You write max outputs here so that you can cap the number of images that are sent in case it becomes infeasible to print them all out. And now we have 25 training data examples. There are ways, I think, to configure this page. Yeah, right here we've got them kind of 3 across. But now we can see this t-shirt and all the other classes. We'll show this in the Tensorboard that comes out. You'll be able to inspect these things. It'll also, I think, automatically put them in multiple pages if there's more than one image, so you can go through and choose page 3 if you want to skip to image 25 or something. Logging arbitrary image data. So here's where we're getting to the customization part. What would be really cool for fashion MNIST data, if you're going to be evaluating your model, which you are attempting to classify these images. You want to know if your model is classifying them correctly. With 10 possible confusers, well, there's one correct object and 9 wrong answers possible for each one. It can be helpful for iteration, debugging, just figuring out where your model is going wrong, to figure out what types of errors your model is making. Maybe it's seeing a shirt and it's thinking it's a coat. Maybe it's seeing this boot and getting it confused with a sandal. There's certain types of confusions that are more likely to occur than others, just based on similarities between classes. The 10 classes are not similarly different. So a confusion matrix is a great way to show that. And for an example of a confusion matrix, I think we can go back to this slide deck here. Is that large enough to get the idea?
Yeah.
Yeah, we can see that what you want when you're building a confusion matrix is you have the truth types are typically put across this is the true class over here, and the class that your model is predicting is over here. What you want is a diagonal full of ones and all the off diagonals to be 0. That's not realistic if you have a less than perfect model. So in this case, what the interesting observation is that when you have a coat is almost always misclassified as a pullover. So it's getting the pullovers correctly when they're there, but then it also thinks that a coat is a pullover. It also thinks that a shirt is a pullover. So pullover is a common misclassification here, and maybe you would look at the distribution of outputs that your softmax model is producing, and you might be able to see, does the pullover seem to be biased a little bit too much in one direction? That might be an observation that you could make from the combination of a confusion matrix and the other information that Tensorboard is able to output. So we go back over here to the collab that we were looking at. Lawrence has provided in the course a pretty helpful plot to image helper function. And the reason for this is that a lot of times the images that we want might be created as plots in matplotlib, which has a figure type. And what we really need in order to send data to the Tensorboard is a tensor. And the conversion between a save fig format and a tensor requires this handful of steps here, where you're reading from this buffer, getting values, and decoding it from this PNG buffer and producing a TensorFlow image, but it's essentially a tensor that comes out. Once you have this tensor image here, you'll be able to feed that directly into your tf.summary.image. Another helper function here, which is going to be used, we won't go into that too much. That one's used actually to create this little grid of images here, where we wanted to see 5 by 5. I think that's what this image grid is doing. And again, once you have it saved as an image, you can just write it out with the tf.summary.image and pass it in as a parameter. And you can put the title here, you're going to call it training data, and that appears right here on the Tensorboard. Once you've built your classifier, again, very simple, we're not even doing anything convolutional here, just 2 dense layers, no dropout this time. We'll use the atom optimizer, a sparse categorical cross entropy. It's a 10-way classification problem, and we'll output the accuracy. And now another helper function, which is generating this confusion matrix. So it's going to need the class names, and it's going to need the actual matrix of values as well. And then it's producing a matplotlib figure. And once it's got that matplotlib figure, I think this function is only going to return the figure. It's using the scikit-learn confusion matrix as its source of input data. And we will use the other helper function to convert that figure into an image tensor that can be printed out directly to your TensorBoard. So if you want to do that with your own custom image like this, TensorFlow provides another cool method here, the Lambda Callback, which enables you to define your own callbacks. So you're not stuck with just the TensorBoard callback or the hparam callback that we saw earlier. You can define your own callback. And here we've got, well, this one's the TensorBoard, regular one, but now we have log confusion matrix, and there's a certain structure that you want to conform to when you're defining a callback. Usually you have epoch and logs as the arguments, and you will be able to, in this callback, call the tf.summary.image and put your confusion matrix image right there in your TensorBoard after you have converted it from the figure to a tensor. Then to create the callback, you just run keras.callbacks.lambda callback and then call this function log confusion matrix on epoch end in the callback. Here for a local TensorBoard, we don't need to worry about the --upload dev because we're not uploading it to tensorboard.dev. We will be fitting, again, a very simple model. The models themselves are not the point of this unit. We're just looking at the TensorBoards. And here we're seeing, let's see, that's a graph there. And we get the, I guess this is a number of screenshots here. We're not looking at the actual TensorBoard. I think if I reran this notebook, I would get that actual TensorBoard. I can do that here quickly. I think it's a pretty quick one to run through. But then when we come down here, we would see the same thing that we've already seen in the interactive version at tensorboard.dev, where you get the interactivity. Any questions or comments? Any topics that people want to discuss on this?
So if I understood correctly, the last few functions you shared is a way for us to customize what we are sharing with TensorBoard and what we are displaying there.
That is correct.
Mm-hmm. Nice.
So let's see. I thought this was interactive in the. This looks like it's producing screenshots rather than the interactive version.
The first one, this one looks interactive to me now. Yeah, this is.
So there is some interactivity here. You can even do a brightness adjustment on a confusion matrix if you want.
Awesome. I like the confusion matrix.
Yeah, it's a good example that shows you how you can build more general outputs that might be more suitable to a particular problem.
nice.
The only thing that I didn't cover here, I didn't know if you or Dimitri wanted to touch it, was the profiler bit through Tensorboard.
I can touch upon before handing it over to Dimitri. Yeah, there's this awesome plugin that I also mentioned briefly in the beginning. We've covered it in our previous session as well, where you can basically analyze performance of your entire, not just model, but end-to-end input to output pipeline. And it's a great way for you. It's basically a debugger. It's basically like in software development, you have like an analyzer profiler. It's basically that. And it looks at how much time are you spending on the data pre-processing, how much time are you spending on the modeling, how much time are you spending on the validation or inference time. And it can even give you some suggestions on maybe your data pipeline or your is very input bound, meaning that your GPU or TPU is waiting for data to be fed to it. And there are some suggestions what to do there. Or where does your model or your input pipeline spend most of the time, and what can you do to expedite things? Like maybe you can use 16 bits instead of 32 bits, or maybe you can use other techniques like TF data optimizations that Dimitri covered, where you can parallelize the CPU and GPU preprocessing. Yeah, check it out. The only challenge we've come across it is that we're not able to run it on Colab. For some reason, we get an error that is trying to collect data, but it's just stuck there. It says accessing data. And I think David Googled it a little bit and researched it. And there's a GitHub issue that is open for that. I think it's a profiler implementation issue. We're hoping to have it. I mean, hopefully the TensorFlow team can figure it out soon, and hopefully people can use it because it's a very useful tool. Cool.
Yeah, I wanted to point the community also to this resource here before we leave Tensorboard. There's a lot of more detailed examples for some other use cases as well. We can get embeddings, word embeddings visualized, word clouds. All of these are tools that are provided, which are not too difficult to access with some of these examples they provide you.
Mhm.
There's also this case of fairness evaluation with the model cards, I think, variety of topics here. What if tool, all part of the Tensorboard package, and some examples here in this Tensorboard guide that I just put the main page in the chat for. So if any of these use cases are interesting, this would be a great resource.
Nice. I've seen some YouTube videos on what if tool. Looks pretty interesting. Yeah, it'd be cool. Maybe we can revisit them sometime down the line. Cool. Anything else you want to share with us, Robert?
I don't think so. Did Dimitri want to say anything about profiling as well?
I was gonna chime in on a couple topics on Tensorboard itself, not profiler. So let me share my screen.
Awesome. Thank you. Thank you, Robert. Floor is yours, Dimitri.
Thanks, George. So yeah, first I was gonna just quickly demonstrate this other functionality we have for visualizing the computational graph beyond Tensorboard, or before we start, before we think about Tensorboard, there is this function plot model in TF-Keras utils, which basically does the same thing, but without going through hassle of having a Tensorboard window inside the notebook. And as you can see, it's basically shows the same computational graph. This is just a small little method to be called. So on the Tensorboard, I was going to add just a couple things. So first of all, I think Tensorboard.dev deserves like a special recognition and then focus. And I mean, kudos to TensorFlow team that they actually put up. This is a separate resource, basically hosts, they say, like millions of experiments already. It's a free resource. And the beauty of it is that you don't have to have a notebook open. And sometimes notebooks get buggy. TensorBoard doesn't always run. It asks you to kill the ports and restart the ports and all of that. Once you upload it here, basically it's a third-party managed service. You can access it from anywhere. Be careful though. When you put there the link, it's going to be accessible to everyone. So there is not like access rights and everything. So everybody would be able to see your models. But I highly encourage to, if you use TensorBoard, to actually use this resource. So one thing one thing it also lets you do is you can download the weights of your model, whatever you visualized, into pandas, which is also I'm not sure if they had it like a few months ago. I don't remember it, but maybe they had. So basically, what you do after you have this tensorboard.dev ID, which is the identification of your particular experiment. So this thing here, all of your experiments are ID'd by this UUID string. So then you can access them and download the scalars, basically the data frame of all the parameters that you want to visualize, but you download them as a CSV or data frame, and then you can do whatever you want to do with with just standard pandas objects, like for example visualize in matplotlib, etc. Sometimes it's more flexible and can be more convenient for people. So I thought this ability to download in a independent format is also something to mention. And one other thing I was going to add, you actually covered most of it, Robert. So was a great broad presentation. So one thing I was going to focus on was embedding. So the let me first see. Yeah. So basically, they have a as Robert mentioned, they have a special section in the TensorBoard tutorial. How to use the embedding projector in TensorBoard, and they what they do, they visualize the embeddings of IMDb reviews data set. So basically visualizing which reviews are close to one another, and discussing the relative distance between different movie directors, etc. So I actually have used this in a practical context. So for one of the projects, it's basically what it does. It visualizes the proximity of different food items, and like you can click on any food item and see how it looks, and the distances between them. So this acts as a your standard embedding space. It just cramps your embedding space, whatever dimensions you may have, into 3D so that we can visualize. And on top of it, it has this TSNE and UMAP and PCA embedding. So right now it's PCAing, right? So I have a 100-dimensional vector attached to each item, like this strudels and everything. Each item has 100 dimensions, and then PCA is used to reduce the dimension to 3D, and then you can do all kinds of experiments and generally understand whether the embeddings make sense or not. This is extremely useful because some other elements in TensorBoard, like the image visualizations and even the the history of your training and testing errors, etc., you can do without Tensorboard. Maybe not as visually nice, but there are other tools. And but for embedding visualizations, I don't there are not that many tools that you have that you can play with and get really nice sort of visuals. And this one is definitely a very handy and very easy one. All you should do is you load your CSVs through this interface, and basically that's it. There is nothing else. Or you can actually mention the paths to your data and to your labels, in the configuration of the projector, and it sort of reads, loads all of your custom data. So I thought this is a cool visual just to add that the Tensorboard can do this type of things too. I think that's it from me.
Nice. That's a cool visualization.
Awesome. Thank you, Dimitri. That was
Sure.
a great addition.
Yeah, we've seen the Tensorboard, the projector in other setups. We've seen it for reviews as well, like positive or negative for movie reviews. But I like the specific data set of food items.
Yep.
Maybe it could be used in a food recommendation app.
Yeah.
Right. Cool. Awesome. Thank you, Dimitri. All right,
But what I
friend.
thought was interesting about that visualization is it really seemed like it was dependent upon the content of the food, not so much the culture where it came from. So you would see foods from the same culture in different places depending on what sorts of food ingredients were in it. That was what I seemed to see there.
Right. So that particular example was glove embeddings.
Mm.
And so, third party, just I downloaded the glove embeddings, and then for each word in the description of the food, I basically, added them up like bag of words, no sequence, nothing. And so each food item with a description got projected into, 100-dimensional vector. So that was basically, but you can do, the way you get your embeddings is secondary here, even if it's a bird or something more complex. Once you have the vector, you just visualize it in the same window, and I find it pretty cool. It's a really nice visual addition.
Nice. All right, friends, really great topics. We're going to switch gears for now. We're going to talk about our last topic for this course and this specialization. Very interesting topic on federated machine learning. Try my best to give us an overview. Again, this is an ongoing research topic, so as well as on the TensorFlow side, it's still evolving as a concept, as well as an implementation. But basically, the core idea is, maybe I should use this graph here that I found on Wikipedia. So you've seen that for most of our models, we are very data dependent as well as infrastructure dependent. We need all the data to be in one central place, and we need our infrastructure, GPU, TPU, CPU, whatever it is, to be as close as possible to the data, so we don't have any latencies in terms of feeding our model with data. And let's say we are training, like Dimitri covered, let's say we want to train maybe a food recommendation app or a food recommendation model, or maybe a classification model where you look at maybe text or images and it's telling us what kind of food or what kind of ingredients that food contains, like Shazam for food, basically. To do that, I have to share my personal data. Maybe I'm using an app on my phone. Dimitri has to share his personal data. Robert has to share his personal data. Everybody has to share our personal data, which is not a good idea, right? Because we have our own lives. We want to make sure that we preserve our privacy when we do this. So, the question is, can we develop some kind of platform or infrastructure where we can collect data from individual users without each of us looking at each other's data or having access to each other's data, or without us being able to reverse engineer where did that data come from? So to do that in this setup, it's called Federated Learning. And the way it works is that we have we have a central location here, what is called like this server, model server. As an initial step, it can start with basically, we're trying to do maybe a regression task here or classification task. Let's say we're trying to figure out classification task here. So we push a specific model to each individual worker. So this could be devices on the edge, this could be our phones, this could be a specific app on our phones. So the server pushes a specific model as an initial. Each specific model here or a more current device has the model and the local data that they can train on. And this is done locally without ever sharing any data or any updates or any gradients or anything like that with other devices. So this is done completely local, and we've seen an example of this with TensorFlow Lite, for example, or TFJS if it's running on a browser. Then when this is done, we want to share results, and these results could be maybe our weights and biases, but we want to share them in a way that this central server cannot enumerate or cannot identify that this specific set of weights and biases are coming from Robert's phone, George's phone, or Dimitri's phone, or Addie's phone. So I want to make sure that they're somehow aggregated, and there's two techniques that federated learning uses in a way that this model server is basically getting an overview of the different training results and not a specific list of individual results. So this way we preserve privacy, but also we get an aggregated result of all the different devices, so that my result and my findings can impact this model server, the central model server, but also Robert findings can impact it, and Dimitri's finding, everybody's findings can impact it. And then that is also now updated centrally. It can also be shared locally, so that I had a specific weight and biases when I was training on my own data, but now I'll be using the average weights and biases from this global computation here. So TensorFlow.org Federated is the place where this project is hosted, and currently it offers what are called two APIs. One of them is the Federated Learning API, and the other one is the Federated Core API. Federated Learning API, think of it as an entryway for us who are TensorFlow practitioners to using federated learning. So if we have existing TensorFlow models and we want to deploy them in a federated learning environment, or if we want to continue training in a federated learning environment setup, we would use this Federated Learning API. And the other one is, since this is a brand new project, the team behind it built it as basically a new language. So this Federated Core API has this lower level interfaces and has its own strongly typed functional programming environment where you can specify specific operations. So you can specify how the data is is collected, or how the data is transformed locally, how the data is shared with a central server, how the data is shared back from the server to the client, and so forth. So if you really want to create something from scratch at a lower level, maybe if you're a researcher, if you want to see, if you want to create maybe different ways to train in a federated way, then you'd use this lower level interface. Just some more context here. Yeah, that's the same API as Lawrence mentioned, the Federated Learning API and the core. Most of it in our notebooks, we'll see them running on simulations. We don't have actual hardware devices or multiple devices to give this a try. It would be interesting to see it in practice, though. And the very basic example that we saw in the course was that let's say we somehow want to. This is just from a measurement perspective. We want to measure what is the temperature or some other reading from our different devices. This could be a tablet or a phone. And each one of our devices has a specific reading. And the way that you mentioned this in the Federated Learning API is the data type. In this case, we're just looking at one number at what is called the placement. The placement, think of it as a role or maybe I mean, they try really hard to not specify location, but in our case, we can think of it as location. The curly brackets just means that you have an array of these multiple floats. So this whole collection of censored readings is basically a collection of numbers, floats, and they're leaving what is called on the client side. What we want is we want somehow to collect that data, create some kind of apply some kind of function to it, maybe like an average function, store that in a central server, and that server now has no idea which device has what reading, right? It's just getting an aggregated value. And that aggregated value can be shared with the devices. So the devices can compare its local measurement with its global average measurement. And the TensorFlow, so the TensorFlow environment has this library that we're going to look at. It's called TensorFlow Federated, TFF. And this function that I'm trying to describe here, where you collect the data, you create some kind of a function, in this case the mean, you calculate it, and you store it to the server. In the Federated Learning API language can be described as floated clients. That's the input of the function, and the output is one number. There's no curly brackets at server. Server is the remote server that does the calculation. What I find interesting is that actually the server does not get the raw data from each device and then calculates the average. The entire protocol, it's a distributed protocol, is in charge of collecting this data and aggregating them and presenting them to the server. So even the server itself never sees the value 68, 70, 69, 70, and so forth. It just sees the result of this. So think of it as the computation is done on the network as it traverses its way from the clients to the server.
Yeah, I thought that was perhaps the most interesting part of the whole topic. Just seeing that protocol, I didn't know that before.
Yeah. And the distributed system were my favorite things back in computer science courses. But yeah, I found this interesting as well. Like the way that the distributed protocol was designed, it also has computational capabilities. It's not just a network stack, just passing data in and out. Cool. Then some other.
And that's really critical for making the model less able to be reverse engineered.
Absolutely.
Right?
Yeah.
The server doesn't actually see the tweaks that each client is producing.
Exactly. Yeah. So privacy preserving is the core idea behind this whole project. Then Lawrence mentioned that basically data is born at the edge. We have billions of devices, phones, IoT devices, and collecting data about them and analyzing it can often help us make better products. So how we're using maybe our cameras, our phones, but it can also be misused at the same time. That's why we want to make sure that everything is privacy preserving. And the other thing is, we want to, if these are edge devices, right? So we'd like to do some kind of inference on the edge. So that means that we don't have to talk to a central device. We don't have to go over the internet. We have lower latency. This can work offline. We've seen that with models deployed on phones where we can do some kind of classification. We don't have to talk to the data center back and forth. Since we're not using any networking, we can have a better battery life. And obviously the most important one that we care for is this preserving privacy as we do any computations. Lawrence mentioned this great project, the Google board, Gboard keyboard, where if you have an Android phone, it's learning from your experience of what words you type together. So it has an idea of what word to predict next. Found that interesting. I'm going to look at it as an example. Not only that, but I think there was a research done that typing on a mobile device keyboard is significantly less slower than on a regular keyboard. So any way we can improve to type faster and get to the results that we want as users would be great. So you might have seen this gesture typing where you're basically scribbling on your keyboard and the keyboard is trying to identify what is the word. So you're not typing letter by letter, but you're holding your finger down and you're traversing the keyboard. And based on where you stop for a second or for a millisecond, based on the different patterns that your finger follows. This Gboard application in the background is trying to figure out what word you typed. You can also do things like autocorrection, you can predict your next word. Obviously, many of us have used also like voice to text. You can just press the microphone button and you can just speak instead of typing it in case your hands are not are busy. So that was an interesting one. Let me quickly mention this blog post that Lawrence mentioned. I think this is from 2017, where the phone itself or the Google Board app is collecting data on how you're typing and how fast you're typing and what common words go together for you. It stores that locally, and this distributed network now is collecting data from multiple devices, but it's collecting them in a way that it's not able to identify what data belongs to what device. And there are two ways to do this. Again, this aggregation is one of them. It's also what is called secure aggregation, where or masking, where if you look at one result, you cannot decode it, you cannot pair it up with a specific device. So this aggregated results or usage is then shared on a central location. That is doing all the heavy lifting and computation of what common words people are using or what common phrases and so forth. Then that central model is shared with all the devices, and that is used as now the version 2 of the model. Some examples here. And this is usually done when your phone is charging or when you're not using it, so that we want to make sure that we don't impact the user experience. So this whole process of sharing data in a secure way, uploading, and then getting an update from the central model. I'll touch quickly on, let's see here. So yeah, this is the motivation behind the Google keyboard. So if you're typing hello, maybe the next word will be world, or hello, your family member or something else. But then how does that happen? How is that trained? This is just a visualization that basically you have the central server here, and you have the different devices. Locally, you know exactly what pair of words go together. So for example, for my device 1, I have the word hello appearing in my, let's say, last week 18 times, world 0. For other devices, this might be a different pair of numbers that when our phones are not being used can be shared, combined, and summed with a central server. And that central server now has basically an aggregated sum of usage. So basically the word is used 2,500 times, the word hello is used 128 times, but we cannot tell which device used how many, which word how many times. That's the preserving part. And this other principle that is important in federated learning is what is called focus collection, where the device only shares data that is needed for the computation. So in this case, how many times, if I use the word hello or world, nothing else. Maybe no other word is shared, or what time, or this, different aspects that you can think of. No, very specific. Basically a dictionary of this key value pairs. This focus collection is another principle of federated learning. And then the server can do any kind of computation, maybe some kind of average, or then can share it back with us, so that now we have an idea of what is our local histogram of words and what is the average histogram of words. So maybe next time I use my keyboard, even though I don't use hello world a lot, maybe world will show up a little bit higher in percentage for me, or more probably. So basically I'm impacted by the population, basically. So the aggregation is one way of preserving privacy, but there's a little bit more research behind it of other techniques of how do we make sure that when devices share data with this distributed network, and the network shares data with the central server, that we enforce even a stronger version of privacy and secure aggregation. there's this paper here on 2017, which basically uses what is called secure exchange of data masking pairs. And these triangles here, this is a very simplified version of the paper. These triangles here mean that individually they don't have any effect on the data. But if I'm trying to do some kind of operation and I have up facing or down in a down facing triangle, whatever operation I'm doing, that data will cancel itself. So that mask will cancel itself. So locally there's a mask applied. I cannot see what's happening, but when I do some kind of operation, those masks can cancel out. So let's see an example here. So I have my individual data and I can apply different masks on them. And I want to share some kind of, let's say maybe sensor readings with a central device. To do that, when I'm trying to aggregate them, based on what masks are applied on my different readings, they will cancel out. So this protocol is written in a way that even if I somehow have access to the readings of this device, it won't make much sense to me. And even if I have the readings of all the different devices, if I did something, if I try to calculate my own, if I try to reverse engineer it, I couldn't, because the readings will cancel themselves out, and only what is designated to be shared with the server will be left. Again, I didn't read this paper. I just skimmed through it really quick. This secure aggregation, privacy preserving ML, but I found that an interesting topic. So yeah, let me take a look. And this is the very first paper that I think that was mentioned, where you have the different devices here in black. You share some kind of updates with a central location. And there's training done on individual ones. And the aggregated results are shared again with the central server. There's a YouTube talk on, I think, Google I/O 2019 on Federated Learning. I haven't got a chance to look at it yet. It'll be interesting to see it. And the other resource they have, the Federated Learning team, have this nice comic book actually, which kind of describes it in a more like simple way of how does this work and how does masking works and how do you make sure that one device does not have access to the other device's data. So I haven't fully read it. I just skimmed through it. I just found it interesting how they're explaining it. That's on the theory of it. If you have any questions, let me know. Otherwise, I'll jump to a quick notebook to see how this is done in code and how things look like from a coding perspective. Again, these resources are again on tensorflow.org federated. So let me just share that in the chat. Cool. So there are two notebooks that are mentioned in the main page. One is this introduction to federated core, which is basically, if you remember, the lower level specification of how things are done. And that goes over the theory and the data types and a little bit of high level explanation. The other notebook, which I didn't get the chance to go through, is how do you actually use this on maybe like a data set like MNIST or FashionMNIST, and how do you make this work? I'll cover this in a high level, and again, I'll share the links for both of them. But for me, the theory here was so much, it was such a dense notebook that it took me a while to go through it. And then again, this is my summary, so I highly encourage you to check it out as well. So first of all, to make this work, we need this TensorFlow federated package. And from there, we're going to import it as TFF. So wherever you see TFF, that's actually this TensorFlow extended or federated, sorry, I shouldn't say extended, TensorFlow federated package. One thing that you will see is what is called this function computation at tff.federatedcomputation. This means that whatever is whatever function follows this decorator, this is a what is called a federated function. And again, this is not, I'll make this distinction multiple times. This is not regular Python. This is not regular TensorFlow. This is its own language, its own implementation, its own protocol, and so forth. So how would I basically do a hello world in federated TensorFlow? It would be something like this. And this is just pure Python at this point. And the only difference is this decorator here at the top. The other thing is federated data. In a lot of examples, the model is what is called like first-class citizen. But in TensorFlow federated, data is actually a first-class citizen, meaning it can be used as input to functions, it can be used as output to functions, it can be used in different transformations, it can be used in different aggregations. So data is basically the core fuel that fuels this platform. And how do I define a very specific point of data or data type in TFF? I use TFF federated type, and the type of data in this case is just a single number, float 32-bit. And this placement here basically says on which part of the network would this live? Would this live on the client end, or would this live on the server end? Has its own attributes and methods here. If I look at the member, or basically the type of it, it's 32. And if I look what is called a placement or the location, it's client. And if I look at the description of it overall as a string, is this list of numbers that live on the client side. The other thing is there's an option where a value, so if I have multiple devices and each one of them is reporting a different value, then there's an attribute for my data type called all equal, that would be false. But if for whatever reason, maybe the server is sharing something with the different devices, and that's the same number, then this attribute of that data would be true. So basically this is how we distinguish between singular number or maybe an array of different numbers. I can do things like struct. That was just a float in the beginning. I can do something like a struct, right? I have basically like a dictionary where I have a key and a value, A, B. And I can use this now as my data type. And if I plot that, that would be a struct of this form, A and B, and they live on the client end. Cool, then this notebook covers a lot about placement and what that means, and basically that you shouldn't think of it as a Python dictionary, you shouldn't think of it as regular Python or as regular TensorFlow. Basically, it's its own implementation in the back end. And some computations which maybe will be easier to understand. So first of all, we declare this federated computation. It expects a federated type of float living on the client as input. And what it does is it takes that input and does some kind of function. This is a built-in TFF function, this federated mean. And if I want to look at the signature of that function, which basically is what is the input and what is the output, it's this. It takes in a single number. There's no brackets here. There's brackets here actually, so it can take a list actually of clients and returns one number at the server. If I want to run it, I give it as input a list that internally will be converted to this TF federated type of float 32. And it will do the average for me and it will return us just a single average value. This is done in a simulation, it's Colab. There's no multiple devices in the backend that share this data with a distributed network. Cool. If I want to do something, this notebook talks a little bit about how this is read during runtime, and it talks a little bit about serialization. So, and that this is not run dynamically. So whenever I write this method, even though I'm not calling it, I'm just defining it, there's actually a process that goes in the back end that tries to read it, and what is called it's being traced, meaning the compiler is figuring out what operations are being used by this method in what order, and that tracing or scanning is done only once. And you consider that just by defining the method, when I run this cell, I'm getting an output of, getting traced. My values don't have values. This is almost like non-eager execution in TensorFlow. It's just the graph being built in the backend, basically, if I can explain that in TensorFlow terms. Then it talks a little bit about you can actually compose. So those are like basic backbones functions. You can actually stack them together as we've seen in other projects. You can create more complicated computations, and that's interesting to see. The other thing that this notebook covers is, so this code looks like TensorFlow, it looks like Python, but it's neither. But let's say somehow you wanted to use specific TensorFlow code, like TF code within TFF. How do you do that? So you can just add tf.keras.layers and let Federated Learning figure out how to do it. To do so, you have to define what is called this, or you have to use this function decorator of tff.tfcomputation. All that says is that this code under this decorator is basically TensorFlow code, and it expects as an input of float32, and it does something. And now this code here actually uses TF, you see here, and all it's doing is just adding a number to our input, 0.5. But the idea is that this is actually TensorFlow code here. So now TFF has to figure out how do I implement this in a distributed way in the backend. If I look at the signature, it takes a float32 and gives me another float32. It just adds half. And now how do I, if I have a list of devices and each one of them have readings, and I'm just adding here half of them. How do I do that in Federated Learning in TFF? So first of all, this is a TFF federated computation that I'm doing. It expects as input one or multiple numbers, and all of them are coming from the client. And then I have this method add half on clients. This is TFF, not TF. And I have what is called a map. This is similar to map functions in Python or TensorFlow. So I'm calculating my function of add half individually for each reading of my devices on the client side. So I'm basically running this map function here, and it expects a list of numbers from the client, and it returns back. Since I'm running this as a map, it's actually will return multiple values, and it will return the value corresponding to each device as a number. I haven't seen a lot of map operations in this book, in this notebook. That was the first time I saw that. I haven't seen a lot of use cases for this multi-input, multi-output case. How do I call this? Again, add half on clients. I provide a list, and if you see, return me another list with each number increased by 5, so by 0.5. This is 1. The output is 1.5, 3, 3.5, 2, 2.5, and so forth. The other thing is you cannot have TF code outside this, a little bit more, outside this decorator. So if I try to do something like this, where I have a TF constant here, but it's outside my decorator, you'll get an error. So it's trying to say you're trying to capture an eager tensor without building a function. So this constant needs to be here. But the thing what we can do is, once we define our decorator and our method, within here, we can code another method that uses TensorFlow. But since this is basically nested underneath my decorator, that is perfectly fine. But the previous case is not, because this is not nested. This is just sequential in nature. Cool. Then this notebook covers a little bit more about different data sets. So we've seen floats, we've seen structs, we've seen native TensorFlow data types. But TFF has also more, as you can imagine, different data set types as well. Like one of them is what is called a sequence type, which is basically a collection of different data types. In this case, float 32. And how do I use, and are they represented? Are they represented by this star? So if I look at the signature or the data type of this float 32 sequence, it's a float 32 star. That means that it contains multiple values. How do I use this? Under TF computation, this is TensorFlow computation. It expects as input a sequence type of float 32. And what it's doing is it starts with a 0,0 tuple, and it's adding to the first tuple my value, the temperature, and the second one is just increasing it by 1. And what we're doing here is basically adding all the temperatures together, and we're also counting how many readings we have, so that in the end we can do something like what is the total temperature reading, which is calculated here, divided by how many readings we had. So that's like our average calculation. So if I wanted to call this, yep, I can call this with a list, and it'll give me the average as well. I can also do this with like ordered dictionary, can have more like, my sequence type basically doesn't have to be a singular data type. It could be maybe an ordered dictionary. So I have a sequence of dictionaries, let's say A, B, and they have a value. And in this case, what I'm trying to do is I'm trying to multiply A and B, but since I have multiple A and Bs, then I want to add them together. So this will make a little bit more sense. So let's say I have this collection of A and Bs and this collection of A and Bs. Let's say they correspond to 2 different devices. I want to multiply A and B. It's 2 times 3 is 6. I want to multiply A and B. 4 times 5, 20. And then I want to add them across devices. That would be 20 plus 6, 26. Yeah, we've seen this as well. So yeah, a lot of this notebook was a little bit heavy on the what I call the language itself, the different data types and what limitations it has, and how can I introduce TensorFlow code within TFF, and how does the theory work at a very high level in the backend. Again, there's a lot of explanations here. The second notebook that I didn't go over to yet, hopefully I'll go over after this meetup, but hopefully this one uses the concepts that we covered, let's say here, of how do we actually train a model in a federated learning way, and how can we use how can we utilize this platform to preserve privacy. I haven't covered it, so I'm not able to speak for that, but that looks interesting. I noticed the TensorFlow tutorial also has this very simple example here as well, so we can check that as well. Cool. Again, I'll conclude with this graph here, where it basically says that our goal is to combine the learning of different devices, but combine them and share them in a way that we are not able to trace back data or findings, but we're all contributing to an average, and that average is shared back with us to improve performance. Yeah. Cool. That's all I had. Questions, comments, let me know before we wrap up.
Awesome. Thanks, George, for this intro to federated learning. This is we just really scratched the surface of it, but a really interesting topic.
Right. Cool. Having said that, I don't think we mentioned this, but all our sessions are recorded, and this session as well will be uploaded on our YouTube page. It's bit.ly DLA TF data deployment here. As you've seen, we started with TensorFlow.js, TensorFlow Lite, data services that took the longest. It was such an interesting and complicated topic. We started our advanced deployment last week, and we'll upload the recording today or tomorrow. So stay on the look for that. After that, we want to open a little bit the floor, not right now, but maybe next week. We'll have a session specifically on hands-on ideas, project ideas, that ideally we would like to use some kind of, or at least one of the concepts that we learned here. So it could be anything related to TensorFlow.js, TF-Lite, data services, or the advanced topics like we covered here, like TensorFlow Hub, TensorFlow Extended, Tensorboard, or even if we're brave enough, Federated Learning. So keep that in mind.
And this will be a happy hour as well. So bring your beverages, and we will not bring our recording devices this time.
Yeah, nothing will be very privacy preserving for sure. But seriously, if you have any project ideas,
it will be a federated task generation or problem conception.
Right. For you who have joined our meetup in the past, we do this every now and then, every after adventure, and we'll actually zoom into our logo here. Our logo is actually comprised of 5 different projects that we did back in the days of working with image data, working with text, working with structured data, annotation, time series. So, I consider hands-on projects and interesting challenges as part of our community's DNA. So please, if you have any ideas, data sets, challenges, personally, I love practical things instead of all cats and dogs. No, do something more useful. So bring them to us, and we will we'll discuss them next Wednesday, and then we'll take a couple of weeks working on them as a team. We'll present our findings. Then we'll have our guest speakers, and I will conclude this awesome journey for us. Cool. I will stop recording here. I will leave the floor open if you have any questions or comments, feedback. But yeah, thanks, Robert. Thanks, Dimitri, everyone for joining. And for you watching online, thank you again, and hope to see you online at some point again. Thanks for joining us. I'll stop recording. Thank you, friends.